In this video, we are going to talk about substitutions in triple integrals, which is from 15.8 section, and this involves Jacobian matrix, which was mentioned before in substitution method for double integrals. So here's the idea. When we look at double integral, we recall a double integral. If we have substitution, for example, you're looking for like double integral, something like this, right? Then what you can do is you can transform that so that by doing substitution, like for example, x equals x uv and y equals y uv, then after that you have different geometric shape for the integral, which I will call that after transformation. It is another shape, which is I call this a tilde, and then f is f, the same, but you want to replace all the x and y's using these functions into functions of uv. But the thing, the crucial part is dx dy. It is not just du dv. After transformed, it becomes Jacobian, which is given by partial xy partial uv, and this is called Jacobian sometimes, and can be computed as xu xv and yu yv, the determinant of 2 by 2 matrix. And the determinant 2 by 2 matrix is simply like these two, the product of this diagonal minus the product of the anti-diagonal, these two numbers. All right, so similar to that, for the 3D object, we can do the triple integral, right? Which is dx dy dz. But if you do this transformation, so you can think of this machine shapes different objects. So after this machine, it will become different object, which I call that G. Then the crucial part is again dx dy dz. So this is basically Jacobian du dv dw. And what is Jacobian here? The Jacobian formula is given here. So often we can write it partial xyz partial uvw, which means it comes with 3 by 3 matrix determinant. So here what you need to know is it's not a linear algebra class, but we can briefly recall how to compute determinant of 3 by 3 matrix. So the determinant of 3 by 3 matrix, suppose if I write this way, maybe I can use another page. So there are many ways we can evaluate the determinant of 3 by 3 matrix, but this is one of the original definition. So this definition is so-called first row co-expansion. So to do that, we can put flipping signs for the first row, plus, minus, plus. So according to this sign, we can put those coefficients in order. A11, A12 but minus, A13 but plus here. A11 here you can put plus, but it's redundant, right? And then you won't fill up these gaps spaces with minors, so-called minors. What is minor? The minor of A11 is the remaining smaller matrix, or we call it submatrix, after deleting the row and column where A11 is contained. So A11 row, A11 column is removed, then you end up with these four numbers, which is submatrix. And so we can write A22, A23, A32, A33. Okay. And next, we look at A12 minor comes here. So what is A12 minor? A12 row, A12 column, A12 row and A12 column. If you remove these numbers, then the rest of thing is given by these two number and these two number, again 2 by 2 matrix. So A21, A31, A23, A33. Now for here, A13 minor is taking away A13 row and columns, and you come up with this 2 by 2 matrix, which is A21, A22, A31, A32. And this one is easy to evaluate, although it's complicated computation, but for each one, this is number times determinant of 2 by 2 matrix. We know what it is. So multiply these two minus multiply these two. And again, for this, the same thing. We can, after we find determinant of 2 by 2 matrix, multiply to A12 and subtract it from the first item. And the same thing here. So this is a little bit complicated computation if you have 3 by 3 matrix to compute determinant. But there's one trick if you have special structure. For example, so determinant triangle matrix is product of diagonal entries. So this is one trick which is often which is often useful for some problems. So for example, if you have like A11, A12, A13, and 0, A22, A23, 0, 0, A33, then this is called triangle matrix, because this is called upper triangle matrix because below this diagonal you get everything 0. So this upper triangular matrix. In this case, this is upper triangular matrix. Then in this case, you don't have to work on co-expansion along first row, which is very complicated. You only need to multiply 3 numbers in the diagonal, and that's it. All right, with this in mind, now we're going to look at, so we know what Jacobian is, determinant of this 3 by 3 matrix, and yeah, we're going to look at this problem. Example. So the example is triple integral. Of course, we can do it without substitution, but we're going to do the substitution, which is suggested by here, and try to use our formula. So first thing we want to figure out is, after this, we want to have dx, dy, dz can be replaced by Jacobian of this form and du, dv, dw. And what is this? This part is just determinant of 3 by 3 matrix. This is xu, xv, xw, yu, yv, yw, and zu, zv, zw. But the problem is here, you don't know what x in terms of u and v and w. Of course, y also. So I need to solve. So this is suggested transformation, but I need to solve it to x, y, z. So you won't solve this as x equals UVW expressions, and y equals in terms of UVW, and z equals in terms of function of UVW. Of course, from the last one, you can see that z is 3 times w, so it's 3 times w. And from second, v equals half of y multiplied 2 both sides, and y equals 2v, y equals 2v, right? And for the first one here, we can see that it is the same as if I divide u to both terms, then this is u equals x minus half y. So you can look at this as u equals x minus y over 2. Then y over 2 is going to be v, right? So that means x equals u plus v. So x equals u plus v. Or maybe I can rewrite that. So one more. So u equals x and y over 2 is replaced by v. So that gives me xyz as a function of UVW. Now from here we can write this Jacobian. So what is xu? Then we can look at here. U derivative is 1, and xv is 1, and xw is 0, and yu, yv, yw, and zv, gu, zv, zw, which is 3. And this is upper triangular because this is diagonal entries, and below the diagonal entries, here below the diagonal, you have all 0 numbers here. So that in this case, we can just do 1 times 2 times 3, product of 3 numbers, which is 6. So now we can write here the integral is basically have 6 du dv dw. All right, next we are going to look at those the shape, the 3D object bounded by 6 planes. So those are 1, 2, 3, 4, 5, 6. So if we look at this, we can do one by one and see what kind of object we have, for 3D object we have in UVW space. So I need to copy this part and to save our time. So we need, so here 6 planes are, first plane is x equals y over 2 plus 1. And second plane is x, y over 2. Third plane, so if you look at 4, it's not just number, it means correspond y. So y equals 4, y equals 4. And again, here 0 means y equals 0. And 5, so look at 3, which means z plus equals 3. So upper bound of z is 3, which is a plane, right? And z equals 0 comes from its lower limit here. So there's 6, so each equation stands for a plane, and 6 planes surrounded an object, so enclosed a region you are going to take integral. And now my transformation I'm going to use is this. So we want to see what kind of object we may have by using this transformation. So here x means u plus v, half y is v plus 1, which means this is u equals 1. And u equals 1 is nice plane, which is, and x equals half y is u equals 0. And y equals 4 means 2v equals 4, which means v equals 2. And here v equals 0. And z equals 3 means 3w equals 3. So w equals 1. So this would be w equals 0. So 6 planes are given by simplified to these 6 planes in UVW space. And this is a rectangular, hyperrectangular, or cubic region. So basically, if you look at this as UVW, then U is from 0 to 1, and V is 0 to 2, and W is 0 to 1. So it's basically gives this cubic area, and integral is simply given by du, dv, dw, and then, but you need to put 6 here, and so this part, and u part is 0, 1, v part is going to 0, 2, and w part is going to 0, 1, and this one means from here we can get this as u, and z over 3 is w, so this is u plus w, u plus w. And if we calculate this, I'm not going to repeat the calculation, but if we calculate, I believe it will be 12. So I will leave the actual calculation for your own exercise, and we're going to stop here.